Impulse and momentum. Impulse force is defined as a force applied for a short time compared to the time of observation of the system. For example, the force that is applied during a collision of a bat striking a ball. Such a force does not change with respect to time. As the bat and ball make initial contact with the forces between the individual atoms of the bat and the ball displace the atoms from their normal position, flattening each object slightly. When the momentum of the ball has been changed enough to reverse its velocity, the contact is broken, and the ball flies away from the bat. So these are different kinds of scenarios of which impulsive forces could act. So one of them would be a ball hitting a stationary bat. The other one would be where a ball and bat are both moving. So how do we define impulse? Well, we know what momentum is, right? We know F equals ma from Newton's second law. So in terms of Newton's second law, we can rewrite this as F equals dp over dt. And how do we do that? What we do is we write m dv over dt, and mv is momentum, and so the impulsive force is now going to be defined as dp, change of momentum per unit time. The definition is going to be the result of the change of momentum of a body is equal to the resultant force acting on the body and the direction of that force. So impulse and momentum. During the collision, the force varies with time. The force is exerted only during the collision from a very short interval from Ti to Tf. Before this, there is no force, and after this time, there is no force. So now we can rewrite that force, the previous equation from the last slide, dp equals sigma f dt. This quantity integration over dp is now going to be called impulse. So impulse now is going to be defined as a force that lasts for a very short interval of time from t1 to t2. And this we are going to call the impulse linear momentum theorem, which is given by the impulse is equals to the force times the duration of the force, or the change in momentum. So the impulse linear momentum states an impulse is a force that acts from a very, very short interval of time, which can also be given by the change in momentum. The statement includes the impulse of a net force acting on a particle during a given time interval is equal to the change in momentum of the particle during that interval. So components of an impulsive force. Since impulsive forces are forces, hence they are vectors, so we need to define them for all the three coordinates that we are used to for vectors. So J net along the x direction will be equals to delta px, which is the component of momentum along that direction. Jx net y will be equals to delta py, which is the component of momentum along the y direction, and so on and so forth. Okay? External forces and impulsive forces, they're going to be, we can characterize a collision as an event in which external forces that may act on the system during the time of collisions are negligible as compared to the impulsive forces. So in external forces, we mean, like for example, gravitational force or frictional forces and all the other forces that are not directly impulsive forces. These external forces may or may not be the same on each of the colliding object. These forces may or may not also necessarily cancel each other. So now let's look at an example. A baseball with mass m equals 0.14 kilograms is moving horizontally at a speed of 93 miles per hour. When it is struck by a bat, it leaves the bat in a direction at an angle 35 degrees above the incident path with a speed 50 meters per second. Find the impulse of the force exerted on the ball, assuming the collision lasts for 1.5 milliseconds. What is the average force? Find the change in momentum of the bat. So first things first. In this particular problem, it's saying that a baseball has a mass 0.01. So the mass of the baseball is 0.14 kilograms, right? And it's saying that it's moving horizontally at a speed of, so it's moving horizontally with a speed of, 42 meters per second. And it says it's moving horizontally, so let's assume that its initial motion is along that axis, okay? And then it says in a direction, it leaves the bat and it's struck with a bat, and then the bat hits it, right? And it leaves the bat with an angle of 35 degrees. So 35 degrees is what it leaves it with, right? With a speed of, so V final will be equals to 50 meters per second. Now what it's asking me to do is find the impulse of the force. So first of all, it's asking me to find what is J. Okay, so note that J is a vector quantity, and it's asking me what is the J on that ball that is being hit. Okay, so what I know is J equals delta P, right? Agreed? However, in this case, if I was to consider this to be my x-axis and this to be my y-coordinate, right, I am going to run into trouble because when it goes back, it has an x component as well as the y component. So what do I do in this case? Well, I know that this can be split into two parts, right? So this will be J of x, which is going to be delta px, and this is going to be J of y, and that's going to be delta py, right? Which implies this is going to be pxf minus pxi, and this is going to be pyf minus pyi. Okay? And then we are going to go ahead and solve these, right? So first case first, we have to find the initial momentas for both of these cases. So let me just find initial PIs for both of these cases. So I will have a PI, P initial X and P initial Y initial. This is going to be equals to mv cosine theta, because the angle is going to be 0. So this is going to be 0, and I'm going to get mv, right? Okay. And this is going to be, there is no component along this axis, so this is just simply going to be 0. Now about my final PF, I'm going to have a PXF and a PYF. This is going to be MV sine theta, and this is going to be MV cosine theta. Agreed? So, what is this going to be? Well, my mass is going to be exactly whatever the mass is, which is 0.14. But what about my velocity? This velocity goes that way. I have defined my coordinates positive that way, so this means this velocity will have an actual negative number. So this is going to be 0.14 times minus whatever this value was, 42 meters per second, to give me the answer equals to minus 5.9 kilograms meters per second. Okay? This angle is going to be 35 degrees, and this angle is also going to be 35 degrees. So I can plug in the values. This is going to be F final, which I can pick up from here. And then I'm going to have my mass be this one. Just plug in the values and solve. So this is going to be 5.7 kilograms meters per second, and this is going to be 4.0 kilograms meters per second. So I just plugged in the values and I solved. So now that I have my initials and my finals, I can go ahead and plug them back into here and be able to solve them. So my Jx, which is going to be here, is going to be that value right here, 5.7, minus that value here, minus 5.9, to give me a total of 11.6 kilograms meters per second, right? This is going to be that value right here, 4.0 minus 0, to give me 4.0 kilograms meters per second. Are we done? Actually, no, we are not done. And the reason why we are not done is because these are the components. How do I find the total J? So in order for me to find the total J, what do I have to do now? How do I go from components into an actual j? Absolutely. So my total j, if I have to find the total j, will actually be equals to jx squared plus jy squared square root. I have a value for jx, I have a value for jy, I can plug them in, solve, and we're going to be, that's how you're going to find the total value of j. And it's going to be kilograms, meters per second. Are we still done? And the answer is no, we're not done, because when we look at vectors, we also have to worry about their directions. So how do we find the direction? Absolutely. Tangent of theta equals jy over jx. So you're going to take these values, plug them in here, solve for theta, and that's going to be your degrees. Okay? I calculate these values to be 12.3 and 19 degrees. But make sure that those calculations actually agree with what you are doing. Okay? Part B, it says, assuming the collision lasts for 1.5 milliseconds, what is the average force? So what is the relationship between this and force? Well, we know, part B, we know J equals F dt, which lasts for a very short interval of time. But in our case, they give us what dt is, right? Which means I can rewrite this as F delta t, which is very, very small distance, sorry, very, very small time. And I have a value of J, which is 12.3 equals F, and they give us delta t to be 1.5. Milli means 10 to the minus 3 seconds. And then you can solve for F, and your answer is going to be right here. Part C, it says find the change in momentum of the bat, which is very interesting because Newton's third law actually says is that the change in momentum of the ball should equal the negative change of momentum for the bat. Okay, so for part C, all you have to do is pick up this value for jx for the ball and this value for jy of the ball, and that will be the change in momentum for the bat as well. So delta px for the bat will now be equals minus 11, I believe that's true, 0.6 kilograms meters per second. And delta py of the bat will just simply be minus 4.0 kilograms meters per second. See? You can't really get rid of Newton's laws when you're talking about mechanics.